Okay, so this spell work is actually somewhat interesting, and it's going to force us to amend what we talked about a little yesterday. Now, my thought on this would have been to take the cube root of y. That would have been my answer, and I would have been very confident in that answer. But it turns out that's not the correct answer, and it's not C either. It turns out the correct answer is to take the log of both y and x. It's a very counterintuitive answer, and like I said, not one that I had on my radar at all. And it turns out, and this is just kind of a good shorthand, and basically, if you have higher degree functions that you're working with, just in general, a good correction for it, a good re-expression for it, is to take the log of both x and y. It's kind of your fail-safe. If nothing else is, if it's just a basic transformation that you could try. And honestly, I'm not sure mathematically why that is, because it would seem to me that we'd want to be looking at cube roots of some kind. But I didn't see a good explanation for it. And I will tell you, this is about as extreme as the like sort of conceptual questions on re-expression goes. Most likely you're going to get a problem that looks like the ones that you had for your homework, where it already gives you a re-expression, and you're just taking whatever your a plus bx, and you're going to have to solve and do what we were doing in class yesterday. That's most likely what questions would be. There could be a conceptual question like this one, and in something like this, just kind of do what you think is best, but it's not going to ruin your grade if you come across a really kind of unexpected problem and unexpected answer. So I don't know what more to say about that, but there we go. A little bit more knowledge. All right, so we are going to look, of course, at inference for linear regression today. There's going to be kind of a lot thrown out today, but I hope it's really not that bad. And if your internet's acting up, no worries, I'm recording, so you'll be able to watch this stuff later. So thanks for letting me know. So we need to talk a little bit about some of the, kind of the foundations of inference as far as linear regression goes. So we're going to just talk a little bit about that. And we're only going to focus calculations-wise today on confidence intervals. So luckily, when it comes down to it, in a lot of cases, the calculations are handled by technology. So there's a lot of this that we need to kind of go through more abstractly what's happening. But when it comes down to the actual nitty-gritty calculations, a lot of it is handled by technology. So I'll give you that kind of as a preface for the whole lesson today. But let's jump into inference for linear regression. And if you read the chapter, you're going to be able to fill in a lot of the blanks that we can't quite talk about. But if you haven't, then you might leave class today with some questions. And my best suggestion for you is to read the chapter, because there's a lot of kind of conceptual understanding that you need to kind of understand to get through, and the chapter has all that information. All right. So, and this is maybe a bold claim here, but I'd say inference has been, up to this point, fairly intuitive. Not to mean that it's been easy, because we have to do some, the nuances here and there can make it a little more challenging, but it's been intuitive in the sense that here's a sample that we have. We want to make an inference about the population based on that. So if we're talking about z-tests, and I could have picked t-tests, but if it's z-tests, I take a sample, I get a proportion, and now I can say, okay, what is the population proportion likely to be based on this? What is the, if I think the population is at a certain proportion, what is the likelihood that that's true, given that my sample came out the way that it did? And that would be our hypothesis testing. So in a lot of ways, if you kind of look at it from that kind of 30,000 foot view, where you're seeing the big picture, a lot of inference is pretty intuitive. So even when we're looking at chi-square, we have a distribution of categorical counts here, another distribution. We're comparing those to see if they match up with what we'd expect. And maybe we're comparing against some standard that's been handed down to us. Maybe we're just comparing two samples. So there you go. It's, again, it's kind of a bold claim, but I think a lot of this has been, from a conceptual level, somewhat intuitive. But at least for me, linear regression doesn't at first make a lot of sense. Like, what does it mean? How do you do regression, or how do you do inference on a regression line? That doesn't mesh with everything we've done so far. So it's a little bit strange at first, but we will see how we can use it. So we've learned some stuff about scatter plots and regression equations. So how are we going to fit those concepts into the idea of confidence intervals and hypothesis testing? Well, of course, that's what you came here for. We will answer those questions. So when we use inference in this context, we're doing one of two things. We can calculate a confidence interval to estimate the true slope of a regression line for the population given the slope from the sample. Okay, now this is going to come up in the presentation in just a little bit, but when we're doing inference, we are only trying to make claims or test hypotheses about the slope of our regression line. It doesn't have to do with the y-intercept. For the rest of regression, we don't care about the y-intercept, okay? We're only making claims and testing hypotheses about the slope. All right, so if we're going to create a confidence interval, so let's kind of think through this a little bit. I've got a scatter plot. All right, this is a sample drawn from the population, and I can easily plug those numbers in. I can come up with a regression line that goes through it. Now, this is not the entire population. This is a sample that I've drawn. And let's say that this is a slope of negative point, what do we want to call that? Negative 0.85. All right. So this slope that I got from the sample, we always call this B, and we're going to come in. We're going to talk about notation a little bit, but our slope is B. Remember, it comes from the y hat equals a plus bx. All right. Now, when I come up with this regression equation from a sample, I don't literally think that this is the true slope for the entire population. So when we're dealing with confidence intervals, what we're going to end up saying is like, well, maybe if we pulled a different sample, our slope would be a little bit shallower. Maybe it would look more like this. Or maybe it'd be a little bit steeper. Maybe it would be something more like that. So what are the range of probable slopes for this, given that I could pull millions of different samples from the population? What's the range? And what we have is, of course, what we're going to end up creating is, well, we're not going to actually create it, but conceptually what we have is a distribution of all the different slopes. And I've got the slope that I actually found, and there might be some variation from that. And of course, this is what we refer to as our standard error. Okay, and we want to say, if we want to be 95% confident that the true slope is going to be captured by the interval that we create, then we might go out a certain distance and say, okay, all the slopes that fall in this range right here are going to be possible slopes, and one of them is likely to be the true population slope. Okay, so anyways, we're going to kind of dive into all these little bits and pieces in more detail as we go through the lesson today. But in confidence intervals, we're going to try and estimate the true population slope for a regression line, because what we got from one sample is probably not going to be the completely accurate one. Okay, and we'll learn about the levers that we can pull to, increase the accuracy of our confidence interval. Okay, now this is what we're going to be looking at tomorrow. Assuming there's no slope and no relation between two variables, we can kind of test that hypothesis and determine maybe that the alternative hypothesis is more likely, that there is an association. And I don't want to talk about that one too much. That's going to be the focus of tomorrow more. So this is, of course, hypothesis testing. We're not doing that today. Okay, there we go. Confidence intervals today. We don't care about the y-intercept, so that's just a restatement of something I've already said. And we only are doing inference on the slope of the regression line. Okay, so we're going to jump down to the conditions for inference. And some of these are going to be from chapters 6, 7, and 8, or 7, 8, and 9, where we are, and these should look familiar. And some of these are coming from all the other conditions for inference that we've been using. So it'll kind of be a mix and match a little. But when we look at our scatter plot, we want to make sure that the scatter plot must not show a non-linear trend. So this is linear, of course, and it's obvious enough. So if we see something like this, we do have the option of re-expressing the data in some way to turn it into a linear trend. And the residual plot, remember, sometimes you have data that looks somewhat linear on the scatter plot, but then you put it into the regression, or sorry, the residual plot, and you can see just a little bit of this sort of curvature, something like this. You can say, oh, well, there's actually maybe an exponential trend to this that's barely discernible. Okay, so the residual plot is another good thing to check. And luckily, that's something that should be provided if that's important for the problem. Okay, so we want to make sure it's linear. Equal variance. When you look at the residual plot, you want to make sure that you don't have a widening or narrowing as you go left to right. You want to have constant variance. So there you go. There's a good residual plot. This is all review, so hopefully you remember this. Oh, wait, skipped something. Okay, normal. A normal probability plot, a normal probability plot must show that the data is approximately normal. So this is something that we did talk about, but it's not probably right at the forefront of your mind as something you recall. So a normal probability plot, just as a reminder, when you have a scatter plot, you can take the z-scores that you end up with, and you can compare them to the expected z-scores. And so what you have on the left here are theoretical quantities, or quantiles, and then here's your sample. And what they do, let's say that this is 200 data points right here, all right? They take, and they have a theoretical framework that says, okay, with 200 normally distributed data points, we should have the lowest be a z-score of negative 1.96. Or this one is saying negative 2.8 something, or negative 3 point something, sorry. Anyways, the lowest one should be at this, and the highest one should be right there. And then all these others should kind of distribute along the way. Those are the theoretical values. If your sample actually follows the theoretical, you're going to get a straight line. And this one follows a pretty close straight line. So this is one that when we see it, we're like, okay, that is a normal distribution of data. So if they give you a normal probability plot, then that's going to be something you can check. They might also give you a distribution. And so at that point, you're just checking the distribution of the points to make sure that it is approximately normal. Okay. So there are different ways you can check normality, but it's going to be pretty straightforward. You don't have to do any calculations on it. You just kind of take information they give you. Okay, the last one, the data must be independent or the sample less than 10% of the population, and the sample must be random. So that's something we can go through and check. Now, we would, in other cases, just call this the 10% rule. We do it a little differently here, only so that we can end up with a nice acronym to help remind us. So we get linear. All right, so linear, independent, normal, equal, variance, and random. So this might seem like it is a little different from the other conditions we had to check. Of course, chi-square had its own check for normality, which was every expected count had to be at least 5. And between proportions and means, normality is checked different ways. So everything had its own little quirk to it, but this one is a little different because we add some extra assumptions and extra conditions that must be met. So if it seems like a lot to remember, in practice, this is not going to be important. All right, you probably won't need to check conditions to make sure that you could conduct a hypothesis test or construct a confidence interval. But it's good to know that there could be multiple choice questions like that. And you, in those cases, if it asks you, have the conditions for inference been met? Then you just need to use your statistical intuition to help guide you through those questions. Maybe you can remember linear, but I don't want to overemphasize that because it's a minor conceptual sort of thing that we have to cover. And FRQs as well are unlikely to focus on conducting an inference test for linear regression, but it's not unlikely that they might have you interpret some data that used an inference test. So we'll see some printouts later, and on those, the inference tests, you might have to read through that and interpret it, like I was saying. Okay, and this is something maybe it's worth spending a minute to talk about. I haven't talked about the investigative task too much. I've mentioned it a couple times perhaps, but the investigative task is FRQ number 6, and it's one that they expect you to spend about 25 minutes on. So it's going to be a time-consuming task, and what this investigative task does is it starts off from a point that you should be comfortable with, something that you know, but then it throws in some new information, something that we will probably have never talked about in class. And yet you should have a conceptual foundation that's good enough for you to say, okay, I can fit this into my framework for everything I know about stats. I can fit this in, I can kind of combine this new information with other stuff I know, and I can use that to kind of investigate this particular problem. And it's actually, I hope it's not intimidating for those of you doing the AP test. I hope it's actually something that you approach kind of like a puzzle, as an exciting thing. I know in a long test, it's not exciting to get a challenging problem, but they're not going to just expect you to know something. If there's a new concept, there will be an explanation in there, and you'll just have to figure out how to fit that concept into what you already know. Okay, so enough about that. Let's focus on this. Notation. We need to introduce a little bit of notation, and basically remember that as we're doing inference, we are inferring from the sample to make claims about the population. And so we need to distinguish when we're talking about the sample versus talking about the population. So if we're talking about the size, the sample size is lowercase n, and the population is capital N. We don't use that much, but we've mentioned it a few times. X bar and mu for mean, S and sigma for standard deviation, and so on. So for linear regression, we have that as well. We've got our B is the slope, and the population slope is going to be beta. Follows the trend of having a Greek letter for the population. Okay, so not much more to say about that one, but keep that in mind. Okay, so this is a starting point that we can go from with confidence intervals. We use the same formula, statistic plus or minus a critical value times the standard error of the statistic. I'm actually going to add this slide on here twice. So the statistic, our point estimate, is the slope we found from our sample. So our statistic is just going to be B. And when we are dealing with scatter plots and data like this, quantitative data, we're going to be dealing with means. And because of that, we're going to have to deal with T critical values and T values and stuff like that for inference. So it's important to know that T star is our critical value, and we will have to check the degrees of freedom, but it works the same way. We don't handle T star any differently. Once we know degrees of freedom, we can approach the problem like we would any other T critical value. Okay. Well, let me go back to that real quick. So we have two things that we can easily fill in. That's B, that's T star. And now the standard error, this is going to be a new calculation, and I'm not going to try and explain all the bits and pieces of it. Well, that's not true. I probably will. Because this formula right here, let me see what okay. This formula right here has a lot of maybe unusual looking stuff in it. And notice that they give you the standard error for your slope, S sub B, and B is the slope. They give you this, but then they have to give you even further explanation to say what S is. So this is what S equals in S sub X. They have to give you this formula. So it's a heck of a lot going on here. And notice that to get S and to get S sub X, both of them, you have to take every single data point and you need to do a calculation for it. So just to get, imagine you had 30 data points, and that's a small sample. But imagine you had 30. You'd have to do 30 calculations and then one final one, so 31 to get S. Then you'd have to do 31 calculations to get S sub X. And then you'd have to combine that in here and do another calculation to get S sub B. This is not something we do by hand. So it's worth it right now just to think about it conceptually. And if you read the chapter, this is something that will kind of make sense for you. But this standard error of our slope is going to tell us, you know, when we have all the range of slopes that are possible, and our sample one is right here, this is going to tell us what kind of deviation we might expect. Oops, it's not S sub B, it's S sub B. So it's basically the standard deviation of this distribution. And we can change what this distribution looks like, how big our standard error is, by understanding where this comes from. And we're going to kind of look at it from a conceptual level. All right, so imagine this. I've got scatter plot, and I've got my regression line. Let's just start with S right here, which is the same as the standard deviation of the residuals, S sub E. In fact, if I look at this, notice that this is essentially a standard deviation calculation, but where I take the actual value, like this point right here, the actual value, and I find the residual by subtracting it from its predicted value. And then I can do that for every residual, every data point, and then I can get the summation of all of that and do the rest of the calculation, and I get my standard deviation of residuals. So what this is essentially telling me is how far from my regression line are my points on average. And so if we had a data set like this, I'm going to add more points that are kind of close to the line. If we had a data set like this, we're going to end up with a pretty high correlation, right? Because we have so many points. I'm just going crazy with adding points here. And our residuals on average aren't going to be that big. So if you can imagine here, we might expect deviations to be pretty close to it. So I can almost think of this as like my standard deviation of the residuals that I'm showing on either side. they would actually be pretty close. But imagine now that my data is actually scattered out quite a bit. All right, so I'm adding a lot more points that are further away. And what this does is now all these new residuals have the effect of widening my standard deviation for the residuals. Maybe now it's sitting about right here. Okay, so the less consistency that there is with my residuals, the more these are spaced out, the wider my standard deviation of the residuals is going to be. And this is going to have an effect on the standard error, okay? Because imagine now, it's easy to think of a lot of different slopes that might fit in. If this is just one sample from the population, maybe I got a different sample that puts the slope like right here or here. But the more tightly it is around the, so those are maybe all possible slopes that I could end up with. But the more tightly these sample points end up around the regression line, the less deviation we're going to get from that. Okay? And I hope I'm not saying this in confusing ways. Now, another thing that can happen right here is this S sub x. This is the standard sample standard deviation for your x values. So what this is really just saying is how spread out is your x data. That's not a good way of saying it, but let's just look at it this way. Here's my scatter plot. I mean, it's got a pretty good linear trend, but it's not very spread out. So maybe if I learn there was some data over here, that's going to change my slope like this a bit. All right. So the fact is, when you don't have a very wide spread with your x, then you're going to have less certainty with your confidence interval on the true slope. But imagine now I had this much data that stretched this out further. And what I have now is a lot of certainty because the line is basically going to have to follow that trend. I don't have the freedom to kind of change it in any way. So the wider that your x coordinates, your x values spread out, the more, the smaller your standard error will be for the slope. Okay, and then for the last little bit right here, it's your sample size. This one's pretty straightforward. If I took this and I added twice as many dots, and I'll just do that, then we have that much more certainty that, you know, this data is, that this trend line is going to follow along. So the higher your sample size, the more accurate it will be. So the highest accuracy you're going to get with your standard error is going to be when you have a set of data that has a wide x range, and that's going to be determined by this right here. It's got a lot of data points, and that's going to be determined by that. And the spread of your residuals around the regression line is very small. Okay, so if I was to turn this into a residual plot, my residual plot would look like this. It'd have equal variance, but I wouldn't see a lot of range in these values. Okay, so hopefully just on a conceptual level that's making sense. Again, this is not something that we calculate by hand, with a small exception. If they give you this value and this value, well, then I could just plug that in, you know, and I could calculate it. And we're going to have an example of that later. All right, so I'm going to pause right there. Are there any questions on what we just talked about? Okay. Now, if any of this is confusing as you are, as we're going through some examples later, anything like that, of course, please stick around. All right, and this is kind of a restatement of what I already talked about. With all the different calculations required to get the standard error, we let technology handle it for us. So sometimes you'll need to just write down the formula just to show, here's my work, here's what I know the calculator is doing for me, but that's about it. Okay, so when we substitute everything in, we get this formula right here. And this standard error is on your AP formula sheet. So when you look at, and now we've covered everything on this formula sheet. So there you go. But anyways, when you look at that, you can find that under the standard error and just copy that over. T star, B is our statistic. The degrees of freedom, very straightforward. When we're doing degrees of freedom for this particular test, let me go back. When we're doing the T star right here, our degrees of freedom that we're going to use is going to be n-2. All right. So that's one difference here. And again, -1, -2 isn't going to probably make a big difference from a numerical perspective, but it's important from a conceptual perspective to show that you know what the correct degrees of freedom is. Okay, we're going to do a couple of examples here, and we've got two quantitative variables, age in years and price in dollars, and we are going to construct a scatter plot of these. And what I want you to do is go ahead, and I'm going to give you some time to do this. I want you to create two lists in your calculator. Part of this is going to be review, but go ahead and put for list 1 the age, and just there was a little bit of confusion to this in 5th hour. This list continues right there, and I want you in list 2 to put this in, and then we're going to go through. If you finish with that and you remember how to do it, go ahead, create the scatter plot. You have to go to stat plot in the top left of your screen, of your buttons. And then you can even try and create the regression line equation. So see if you can remember how to do that. And anyways, take some time and we'll talk again in a little bit. Okay, so it's important to remember how to put this in and how to use the calculator to come up with a scatter plot and to calculate your linear regression line, the equation for it. And we use a plus bx, b being our slope. So anyways, hopefully everyone was successful with that. We don't need to worry about the regression line for our particular problem, but maybe that would be important for a certain problem that came up. But for right now, we're going to construct a confidence interval, and so that's all well and good. The last little bit right here, it says check the residuals to see if conditions for inference are met. Now, I'm not going to make you guys create your residuals, though you can construct a residual plot. Your calculator can do that. It remembers the residuals when you do your regression analysis, the linear regression. But I am just highly skeptical that you're going to see a problem like that on your AP test. So I'm not going to worry about that right now. Almost all the questions I've ever seen, maybe all the questions I've ever seen dealing with residuals, they show you as residual plot. They don't expect you to create it. Okay, so let's kind of, that was review, part 14, but we're going to use this problem, and you already have the data put in. And now we're going to look at problem 16. And this is the key part of it. We are going to create a 95% confidence interval for the shape or for the slope of regression line and explain what your interval means in context. So it's good to kind of get into the habit of putting this into, you know, the full format here. So if we're going to state what we're doing, we've got, we're basically just going to create a confidence interval. So I'm just going to name, so my, sorry, kind of spitballing here a little bit, but we've got our confidence level is going to be 95%. We're going to, we don't really have hypotheses we're testing right now. So we are going to be testing for beta, or inferring about beta, which is the true change in price per unit or per year. Okay, so that's what we're estimating here, is the true change in price per year. And I put the S here for state plan. I'm going to do a linear regression. Dang, I keep hitting my screen in weird ways. Linear regression T interval. Okay, my conditions. Now here's where we need to. So my conditions, again, we probably won't need to do anything like this, but is it independent and random? It doesn't say, but it's classified ads in a newspaper. You could argue that it's not random or independent or something like that, but I mean, it's less than 10%, we're good there. But is it random? I don't know, we could make a comment about that. I want to keep emphasizing it's unlikely you're going to have to actually do something like this. Linear. Well, we saw the scatter plot. It looked linear to me. Is it normal? Well, we did not check, and I'll just put a question mark right here because we really didn't have the proper tools to test normality. We didn't look at distributions or anything, but anyways, and then is it equal variance? We didn't check the residual plot. So if you did have to do something like this, you could go further into it and you could construct a normal probability plot. It's possible you could construct a residual plot. I don't want to emphasize this too much because it's unlikely you're going to need it. All right, so do my calculation is the stat plus or minus a critical value times the standard error. My specific formula is going to be B plus or minus T star times S, and you can even put S sub E over S sub X times the square root of N minus 1. And we don't have those values. I'm not even going to plug it in. I'm going to let my calculator do the calculations from here. And this is where the new stuff comes in. So you already have your two lists made. What I want you to do is go to stat, test, and down at the very bottom, option G is your linear regression T interval. And so you can click on that, and you've got your X list and your Y list already populated with list 1 and list 2. And age is our X, it's our explanatory variable. Price is the response variable. The confidence level is 95%, it's already preloaded that way. We can calculate it. And now I can just show my answer. It's going to be negative 1,099 to negative 819.5. All right, and then I can conclude. So it's important to realize that this has real world meaning, all right? So because we're looking at a slope that in our scatter plot, and maybe we could even show the scatter plot as part of this, but in our scatter plot, we don't know that this is the true slope, downward slope. So what we can think about is the fact that slope represents a change in Y over a change in X. And in this case, it's going to be dollars per year. Those are our units. So the slope, whenever we look at it, it's like negative 959. 0.05. We're saying that we expect this car to lose about 959 dollars per year. So it comes back to a real world kind of explanation. So here's how we can kind of conclude this. We are 95% confident that the interval from negative 950, or sorry, negative 1099 to negative 819.5 captures the true change in car value per year. And that's it. Any questions on this one before we move ahead? Okay. So what was I going to say here? I felt like I was about to say something that I forgot. So there we go. Let's look at another example. So when you have two lists, you know, the calculations are actually really straightforward and easy, but you know, we have other examples, and this is something that it might be a little bit challenging as we go through this. So this is not two lists. In fact, what we have are a lot of displays, and we've got this big printout right here of a bunch of numbers that now we have to interpret. When we did this before, the only stuff we cared about was this right here, maybe the r squared, and that's about it. But everything else we didn't care about. Now we're going to be looking at a lot more of these numbers, okay? And the first thing maybe we can do is we can check the conditions for inference, all right? So this is not a bad one to do because it gives us a bunch of displays. We can do that. So is it linear? I'd say it's not non-linear, so sure, it meets that. Independent and random, I will assume those are the case. I know independent is, or it's 10% rule has been met. Random, I'm going to assume it has been. I don't see the word random, but there it is. I'm sure it's random. Normal, now we've got this. Look at our residuals. We can see this right here. This kind of gives us a little bit of an, I think this shows pretty well that we've got some normality going on. And then equal variance. This one's maybe the weirdest. It's almost like a ball of data right in the middle, but I don't see a very clear widening or narrowing of the data. So it doesn't look pretty, but I would say that it doesn't violate the equal variance. So we're good on the conditions. So now we want to construct a 90% confidence interval. So stating, I want to find beta, which is the true change in math score per unit of verbal score. And my confidence level is 90%. I'm going to skip the checking. I kind of already did that. So I will do the linear regression t interval. I checked my conditions. Do. So now this is one where we actually have to do some calculations, and we're going to need to find some data. So let me just start off real quick. Stat plus or minus the critical value times the standard error. And this is going to be b plus or minus t star times s sub e over s sub x and the square root of n minus 1. So we need to come over to our printout and find these values. B is the slope. If you remember, there's always the y-intercept, which is going to be labeled with either intercept or constant. And so I know that this coefficient is my y-intercept, which means that this one it must be the slope. So I'm going to get 0.675 plus or minus. I'm going to come back to t star in a second, but I do know it's going to be t star of, or actually I'm not going to write it there. It will be t star of, my degrees of freedom is going to be 162. My sample size right here is 162. See that? So here's my degrees of freedom, 160. So we'll look at that in a minute. But let's kind of plug in the other stuff. The standard deviation for our residuals, well, let's kind of look at that real quick. That's given right here. Notice it just calls it S, and you can call it just S if you want. But that's 71.75. And the standard deviation of our X. Keep in mind, verbal is our explanatory variable for this one, so that's our X value. And up in this part of the printout, it shows us our standard deviations. So since verbal is my X value, the standard deviation I'm looking for is right there. 99.5199 times the square root of 162 minus 1. So now the only thing we need to find is that t star of 160, and this you can refer to your table B, the t table. And I'm not going to switch over to that because I don't want to lose our writing. But if you look at it, it's not going to have 160 on there. So I'm going to round this down to 100 and look at that row. And now I can say with 100, 90% confidence level, it's 1.660. I believe that's right. So this one's a little bit more complicated. You can see where we have to actually find the numbers from the printout and plug them into our equation. But at this point, we can just plug this in and do the calculations. And we don't have it nice on the calculator where we can just plug the data in. At least I don't know how to do it. There might be some extra thing you can do. But I'm going to calculate the standard error first of all. So that's going to be what's in the parentheses on the far right. All right, and when I just did that one part in parentheses, I got 0.0568.
And so if the dependent variable was verbal, then we would use like the standard deviation of math and stuff, right?
Yeah, and it would have calculated, the printout would have been different, where it would have been math right here, and we would have had some different numbers to work with. I mean, these standard deviations would have changed, but yeah, we would have used the math standard deviation for S sub X.
Okay.
Yeah. So I wanted to point out, and maybe you noticed this number that we just calculated, the 0.0568, is already on the printout right here. All right, and so you might be wondering, why did we show all this calculation, do all that work if the number was already there? And you hopefully know the answer. It's to show the work. It's because otherwise you're just letting the calculator do everything. So you want to show how this number was arrived at. I wouldn't recommend just taking this 0.0568 right here, which you can see is the standard error. It's labeled as such right there, of your verbal, which it really is saying of the slope. Okay, so anyways, we've got this, we've done some math. Now we can just finish the calculation. I will go ahead and just show what my confidence interval I got out of this. 0.6. All right, I don't really have room. I could kind of squeeze it in, but I'll just kind of get it started. For the last little bit with the conclude, I would say we are 90% confident that the interval from, let's put dot, dot, dot at this point, from 0.581 to 0.769 captures the true change in math score per unit verbal score. All right. So hopefully now it's making sense of how all the stuff we learned about confidence intervals now can apply to linear regression and scatter plots. Okay. I do have a question like this on your homework. I will go through it. I guess before I do, were there any questions on that last one? Okay. This we don't need to do another calculation for, so it's really just a conceptual one. I don't even think I'll write anything down. But the output reports S as 46.16. And I guess we need to know the context. This is, does a person's cholesterol level change with age? So we've got this regression analysis that was run. And so the, what's the word I'm looking for? The explanatory variable is your age. The cholesterol level is the response variable. So anyways, S is the same, remember, as S sub E. So this is the standard deviation of our residuals. How far are our actual data points from their predicted one on average? So on average, a person's cholesterol level will be 46.16 off of the predicted value. All right. The next one, what's the value of the standard error of the slope of the regression line? Well, again, that's right here. The regression line, and you can see the standard error, so it's 0.2574. And explain what this means in context. If we took a lot of samples, then on average, the slope would vary by 0.26 up or down from this 0.77. So if we did this again and we got a 0.90, that wouldn't be unexpected. But if we did this again, we would not expect to get a 1.5 slope, or we wouldn't expect to get a 0.28 slope. So these would be unexpected. We would, so the average change, you could kind of think of the average variation from the slope that we got would be 0.2574. All right, and to visualize that, and this will be the last of it, 0.2574 is a slope about like this maybe. So a slope, oh, I'm sorry, that's not our slope, that's, I'm doing this wrong. Our slope is 0.77, so that's gonna be more like that, okay? So a change to a to a one slope, which would look like this. Actually, I'll do it all from the starting point. So if our slope looked like this, down to about this right here, that wouldn't be unexpected. But this right here, we wouldn't expect our slope to fall in this range at all. Okay, so I hope that's enough. Hope I didn't over-explain or confuse you with anything that we talked about today. Your homework is right there. Read chapter 22 because you might still be confused at the end of class today. Chapter 27 will do a lot to provide some extra information, fill in some of those blanks. Okay, tomorrow we're going to do some hypothesis testing. If you have any questions, stick around. Besides that, have a wonderful day, and I will see you tomorrow.